And our next speaker is Marco Jacobs. Marco is the Technical Marketing Director at Videantis and has over 15 years of experience in semiconductor, IP, and multimedia applications. He's going to be focusing on a specific object detection technique, the histogram of ordered gradients, and in particular how it can be implemented on a low-cost, low-power processor.
Hi, everyone. Thank you. Okay, so I'm going to be talking about one specific algorithm, the HOG algorithm that's combined with an SVM. Let's first step back a little bit and think of where we're coming from. Jeff mentioned this this morning too, but it's a really interesting fact to me is that, and Jan mentioned this also, that the brain actually, half of the brain we're using for vision analysis. And so we do a lot of things with our body, etc., and half of it apparently of our brain we need to do vision analysis. So it's a very compute-intensive problem also for our brain. And if you look at the power consumption, I think of our body as being fairly efficient, but we use about 100 watts to keep ourselves warm and to do all these mechanical things with our body. But the brain uses about 20 watts. So this means for computer vision that we do all day long as soon as we're awake, we use about 10 watts. So now it's really the challenge to bring this down to a mobile platform and to bring this down to milliwatts using semiconductor technologies. One thing though is that, so that's going to be quite a challenge. The nice thing though is that we don't have to beat the brain into everything. You know, when we're building consumer electronics and computer vision devices, we just have to beat the brain into in a few specific areas. Maybe we want to just make it faster. We want to make cars safer. Maybe we just want to make things sometimes cheaper labor than using humans. So I think that's quite doable, and you see that the industry is marching forward quite quickly to make that happen. So object detection and object recognition, what does that do? So what things that you can do with object detection typically is recognize an object. So like, is this a person? Not who is it, but just is there a person there, or is there a car in view? If you look at one of the computer vision books by Richard Selesky, which you can find online actually for a free download, one of the chapters is about object detection, but it's one of the later chapters, so it's maybe a little bit more complex than and a little bit further on than the typical filtering and feature detection and feature tracking and all those kinds of algorithms that he describes in his book. So the specific algorithm I'm going to be talking about is the histogram of oriented gradients, and this is from 2005. So it's 9 years old, almost 10 years old, but it was really a big step in computer vision, and it's still used quite a bit. And at the time, Dalal said it provided about 100x accuracy increase in object detection. So it was a big improvement on the state of the art at the time. So let's look at some sample applications. What it's used for and what Dalal and Triggs focused on was on this pedestrian detection for automotive applications. So is someone stepping in front of your car, or as you're backing up, is there someone behind your car that you maybe missed? But it can also be used for vehicle detection or in surveillance for perimeter detection. This morning we also saw in biology, it's nice for people who do research in biology to automatically detect if there's an animal, to count them, etc. And of course also in the industry, production industry, machine vision, and image categorization, but many possibilities there, and many different applications that can use object detection. But we're going to focus, similar to the original Dalal and Triggs application on pedestrian detection. So there's basically two steps in this in HOG. The first step is to train this classifier. So, and this you do offline. So what you need is lots of images. And what they did is they annotated lots of different pictures of pedestrians so that, and say this is a pedestrian and put that in. The image first gets normalized. You scale everything to a fixed resolution. And then for each image you extract this feature vector, and we get to that in a little bit more detail later on. And then you have this classifier. So that's basically one long vector that you multiply this feature vector with. And if it's bigger than a certain value or smaller than a certain value, you know you've detected an object that belongs to this class or not. And that's the part you need to train. So first of all, you train it with your images that you know have a pedestrian. Then often what they do is they take an image that you know there's no pedestrian in that image, but then actually you can reuse that image. So you can crop it in different ways and maybe generate a lot of different images out of that if you know there's no pedestrian there, and also use that as your input for a reference data where you know there's no pedestrian. And then as you train it, there may still be false positives, so it's important to put these false positives also back into your training material and annotate those with, no, it maybe looks like a human, like a pedestrian, but it's not. So this training is offline, it takes some time, and once you're done, then you go into your real-time process, so where you're trying to detect these pedestrians. So from a high level, the way the algorithm works is you get a single image in, so it works on one image at a time. You first build this multi-scalar pyramid. So with the original image, it's a little bit smaller resolution, smaller resolution, smaller resolution. And then you're going to move a window across each image at all these different levels, at all these different scales, extract the features, run your classifier that says, yes, this is a person or no. And then you may actually detect the same person multiple times, so maybe at a slightly different scale, or a slightly different position. And then you have to fuse these, say, no, actually that's the same person because they're so close. So you detect those as one, and then you have your final object. And just some examples of the input data that they used. So they're just typical pictures of a person in a variety of poses and different illumination, different backgrounds, mainly upright people, but not heavily massaged input data. So this is really real-world images. And as I was going through this data set, what was kind of interesting to me is that, so this work was done at INRIA in France. And apparently there's quite a few people who smoke in France, because I saw quite a few people holding a cigarette. So if you have if it's not detecting you for some reason, then maybe you should hold up a cigarette and then it'll recognize you. So let's go again in a little bit more detail on how this works. So first of all, your image, you're not looking at color data, so we're just doing grayscale input. So convert to grayscale first, and then you're going to build this multi-scale pyramid. Then you slide this 64 by 128 pixels wide window across this whole image and across the different layers. And for each of these 64 by 128, you're going to do a histogram, and we'll get in a little bit more detail. So at the highest level, it's a 64 by 128, and then within the 64 by 128 window, you slide a 16 by 16 window, and you're going to calculate these histograms for each of these positions. So here you see, where you slide this 16 by 16 window, and the 16 by 16 window, again, is divided into 4 blocks of 8 by 8 pixels. And for each of these pixels, you calculate the gradient, so the direction kind of of the slope, and how steep the slope is, so the magnitude, and you put those in a histogram. So for this 16 by 16 block, you get actually 4 histograms, and typically this gradient is divided into 9 cells. Some people use fewer cells, maybe 8, but the original paper used 9 cells. So you're going to do a histogram, and at the end of it, you have for the 64 by 128 window, you actually have almost 4,000 data points if you add it all up. So you have these 7 times 15 positions, 105 positions, and if you multiply that all by the histograms, then you have about 4 kilobyte, or at least roughly 4,000 elements, and that's the feature vector for just this 64 by 128 pixel window. And then you do your multiplier by the SVM. So this is just a dot product, and then you know whether you detected someone in that location. So it's a huge amount of processing if you think about it. But it works, and it's doable in real time. One thing that people often do, since it is a lot of processing, is to combine HOG with an optical flow or feature detection optical flow algorithm. So this means you're going to only do the full HOG maybe once every 30 frames or so, or once every 15 frames. You detect your pedestrians, and then the next several frames, you're just going to follow the person. So you do a feature detect just within that window, and then follow all these features from frame to frame, and then this actually significantly reduces then the processor load. And another thing this gives you automatically is the direction that the person walks into, or if these features expand, then you know something is getting closer, or if these features contract, then you know it's going away from you. So that's all about the algorithm. Now I'm going to be talking about how do we efficiently map that algorithm onto our own processor. So similar to the previous speaker, videantis, so the company I work for, our product is a processor, a DSP processor, that's very good at these kinds of pixel operations, at these kinds of vision algorithms. And I'm going to be showing how we do things a little bit differently. So if you look at our architecture, we have 2 different processors. One is what we call the SP for stream processing. We use that one solely for video codecs. So it's very good at bitstream packing, unpacking, but you don't really do any of that kind of work when you're doing computer vision algorithms. But the MPs are the processors that we have that are very good at these pixel operations. So we have an array of those. And each MP is a small VLIW engine, small SIMD engine, and it delivers about, at 800 megahertz, delivers about 25 giga operations. It's still very small, so I'm not sure how many people here are in semiconductors, but it's always about being small, because if you're small, then that means the cost is lower. So for this whole architecture, we're less than 2 square millimeters in a 28 nanometer process. Now, if you look at also on the show floor, what I saw, where do people do these kinds of vision algorithms? Where do they run them? Typically, you have these 3 different categories. One is just on a host CPU. Another category, like an ARM or x86 host CPU. Then GPUs, which used to be able to just do 3D graphics. Of course, now you can use them as general purpose processors. Then you have imaging DSPs, and there's different vendors there. And then here's where the last column is our architecture, and I'll show a little bit how we differ. So if you look at the levels of parallelism, at the lowest level you have this the ILP. So how many operations in parallel, or how many instructions can you execute in parallel? So we've decided to not do too many in parallel. So we have a 2-issue VLIW. If you go wider, like some of the imaging DSPs have, there may be 4-issue, 5-issue, or maybe even wider. TI's C6 is a 8-issue VLIW. Then you need to start doing a lot of loop unrolling. There's lots of no-ops to fill all these slots. So that actually gets inefficient. With a SIMD, you can decide to go very wide, and that means you just have a single operation, and then you immediately execute that operation on a very wide vector, so a lot of data. But by lots of algorithms, and we saw that in the previous presentation also, it doesn't map really well. So you have to do a lot of extra things to make sure you can execute this single operation on a lot of data. So we decided not to go too wide, so we're a lot narrower than some of the other vision and imaging architectures. So we do less processing per cycle per core, but then what we do is we decided to have multiple cores. One of our architectures that we have in silicon and that we are demonstrating here has 8 of these MP cores, and they all work together. And that means it's a very flexible architecture because each core can work independently. And that also means you can easily scale. So you can select fewer cores if you want to be really small, and resolution is not that important, for instance, to operate on lower resolutions. Or you can select more cores, so it's a scalable architecture. Or over time, maybe when you say, my second chip is out, and I need to have more performance, then you can just add more cores and scale that way. On the processor frequency, the medium pipelines, so not very long pipelines, make sense. Of course, a host processor often has a very long pipeline, but that introduces quite a bit of overhead for these imaging algorithms. And also caches. Caches are nice, make it easy for the programmer, but it means the hardware needs to decide where to move data, and the hardware doesn't have any knowledge about the algorithm, so it's better to actually not use caches. It makes the architecture a lot smaller, and we also have a DMA per core, so it's under programmer control, and since we're embedded, it's all about low power, making things small. We believe the programmer can better make those decisions to make sure the data is very efficiently moved through the processor. So we've integrated our HOG algorithm with OpenCV. We do quite a bit of work with OpenCV, very commonly used library. And it's actually very easy if you're writing, let's say you have a whole OpenCV application, you're calling, or a vision application that uses a lot of the OpenCV routines, and you want to enable our accelerator, then you can just add a few lines of code. So basically, when you're allocating your data, you say, let's put this data in a space that's also available to the videantis accelerator. And from then on, while you do the allocation of your memory, the rest of your program you don't have to change, and automatically under the hood, inside the API, we make sure that all the processing is offloaded to this to the videantis processor. So let's look at how we implemented HOG. So there's first the pyramid building, and then there's the extracting the feature vectors within the HOG algorithm. So we need to split up the data across the multiple cores. So the way we do it is you look at the input image, and we split it up into rows of 16 pixels high, and within this row we calculate this HOG feature vector per 16 by 16 block, and we slide these blocks while DMAing in data. So you DMA in your data and you slide the block over into your processing. So kind of a double buffering to make sure you're pulling in this data in the background and your processor isn't waiting for data. For the SVM step, it's a little bit different. So here, actually, on the demo, what we're using is we're not using the 64 by 128 window, but we're using a slightly smaller window. That's from the Daimler detector. So from Mercedes, they use a slightly smaller window because then you can detect also objects that are slightly smaller in view. For this processing step, we actually operate in columns. So here we split up the image into multiple columns, and each of our MP processors executes and processes is the single column. So again, shifting it down every time by a line, doing the DMA in, and then processing on your previous block. Now let's look at performance. If you look at the hog, and we have it implemented in silicon at our booth, when you run it on VGA resolution, we need about six of our cores at 400 megahertz. So that's in a 40 nanometer process. So that consumes about 30 milliwatts. So here we see it's really low power. And if you do this trick of only doing the full hog once every 30 frames, then obviously it scales down by a factor of 30. So then to do hog goes down to roughly 2 milliwatts, or you can do that on one core. We can scale up in resolution, so for 720p, if you're targeting a newer process, so maybe 28 nanometer, we need 8 cores, and we can implement that at 800 megahertz. So since the 28 nanometer process uses a little bit less power, the power doesn't go up that much, so it's about 40 milliwatts. If you compare that to standard ARM, then an ARM runs VGA at roughly 1 frame per second, a Cortex A9, but it runs at 1.2 gigahertz. So if you compare cycle for cycle, you see that the performance on our processor is about 100x a standard ARM. And if you look at power, since the ARM has all these caches and longer pipelines and much more overhead, since it's really built to web browsing or run an OS, the power is even a bigger factor. So we're about 400 times lower power than a Cortex A9 on this algorithm. Okay, so that's the end of the presentation here. So the conclusion is Hog is still a key algorithm for object detection. This morning, Jan showed this deep learning algorithms that there's a lot of potential there, so that's interesting. Still, Hog, what we see is we have a lot of customers asking for it, and so it's still a key algorithm. It detects, so there are some false positives, but there's about a 90% detection rate. So probably you need to do a few more things around it if you really want to get to 100% accuracy. The algorithm is very demanding. It's about 10 times as complex as feature detection or optical flow on the full frame. And we've seen that we have a very efficient implementation on our vision processor. So please stop by our booth, and thank you.